In this lecture, we will be speaking about the pumping system and pumps. From start to finish, pumps play an important role in all water distribution systems. At the source, they help deliver raw water to the treatment plant. They also supply water to sections of a distribution system where it is not possible to supply by gravity. They also add appropriate chemical doses during treatment. They transfer sludge from settling chambers for further treatment and disposal. So the main parts of the pumping system consists of pump. Active part is a pump to provide increase of pressure and potential energy in passing of friction loss within the piping system. The second important part is the pipe. So the inseparable part of this system is the pipe with armatures, suction and discharge pipes which present passive part. Energy delivered by pump is consuming it. The third important part is our suction and discharge tanks. So from the suction tank, the well accumulation reservoir is the water pumped to the discharge tank. So the water tank, pressure tank and accumulation tank. These parts are marked above with control room, flow meters, water level indicators, equipment for reduction of water hammer in unexpected shutdown of pump. They all form the pumping station. So here that's my suction pipe, this small part, that's my suction tank. That's my pump. It is used to add energy, to push the water all the way to the discharge pipe right here. And that's my discharge tank. So the different types of applications require different types of pumps. Pumps are selected based on system requirements, discharge pressure requirements, flow capacity required, and availability of space. The two most common pumps in the water industry are centrifugal pumps and positive displacement pumps. Centrifugal pumps are used most often in water distribution, while positive displacement pumps, like plunger pumps, rotary pumps, are most often used in treatment plants for chemical dosing. So here it shows that the pumps are very crucial because they supply water to sections of a distribution system where it is not possible to supply it by gravity. So now I'm going to be speaking in details about the positive displacement pumps and the centrifugal pumps. So for the positive displacement pumps, coagulants added in exact doses into treated water. It's mainly used for chemical dosing. While for the centrifugal pumps, the centrifugal pump was invented by the French physicist Denis Papin in 1698, and today this type of pump is the most widespread in the world. Centrifugal pumps are the most common type used in water distribution. Centrifugal pumps have a circular fan, turbine-shaped structure called an impeller that is mounted on a centrally supporting structure called the shaft. The motor rotates the shaft and can be powered by electricity or diesel fuel. Water enters at an opening in the center called the suction. The rotating impeller imparts high velocity to the water, and it is circulated and thrown outward. A circular-shaped covering called casing surrounds the impeller. The casing is shaped like a spiral so that the water slows down, and the velocity head is converted to pressure head as it flows out of the casing. There are three main kinds of centrifugal pumps that are the most often used in water distribution systems: the horizontal centrifugal pumps, the vertical turbine pumps, and the submersible pumps. Water supply pumps can be installed in two ways. They can either be submersible in a well or they can be placed on the ground surface. Now here we are going to be speaking about the basic hydraulic parameters of the pumping system. We are the capacity or the flow, the specific energy, and the head. Those are the three main important parameters. Capacity or the flow, it is a volume, flow rate, or more conveniently, flow rate. Capacity is defined as the volume of the liquid per unit time delivered by the pump. It can also be described as the volumetric flow rate of the fluid being transferred. The most common units for capacity are usually cubic meters per hour or gallons per minute. Specific energy and head are two terms that are often used in pump systems. The specific energy is the amount of energy what is given by pump to liquid between suction and discharge nozzles. There are 4 forms of energy in pump system: pressure, elevation, friction, and velocity, what are necessary for transport of water from suction tank to discharge tank, for passing of different pressures and different heights in suction and discharge tanks, and for passing of friction, what is caused due to the movement of the liquid through pipes and fittings in the system. So the specific energy is the summary of these 4 energy: Yp, Yg, Yk, and Yf, where Yp stands for the pressure energy, velocity energy, elevation energy, and friction energy. The specific energy Y we can express as the summary of specific energy on the side of the suction and the specific energy on the side of discharge, a summary of all 4 energies. So Y is equal to, here we have the pressure energy, the elevation energy, velocity energy, and friction energy is right here. So we can see it again: pressure energy, elevation energy, velocity energy, and friction energy. In case of pumping from a tank where on the level of the water is atmospheric pressure, the well accumulation storage to the tank where it is the same pressure, we consider that PA1 is equal to PA2. It means that part of the formula expressive pressure energy will be equal to 0. The same we can consider with velocity energy, because different velocities in suction and discharge pipes is negligible. So in this case we can summarize the formula as the following: Y is equal to G times ZA1 plus ZA2 plus the friction energy, so elevation energy plus the friction energy. The relation between the specific energy Y and the total head, total pumping pressure H, expresses this new formula, where G is the gravity acceleration times the total head. The pump power is a shaft power transferred from the motor to the shaft, and it's defined by this relation, which is a PU output power divided by the efficiency. P is calculated as follows. You can see the P is measured as follows, and pump efficiency is calculated as the following. So efficiency is equal to PU over P. Efficiency of the centrifugal pumps is approximately from 60 to 65%. Very important is to know the supplied power from external electricity source to the motor, P motor, given in watts. So P motor is equal to the P over my efficiency of the motor in this case. The basic hydraulic parameters of the pumping system to interact, and these dependencies express pump performance curves. So this is my head, this is my flow rate, and this determines the performance of a pump. The performance of a pump are very important because many catalogs have these curves, and these curves help us identify the performance of pumps. So this is how the pump performance curves look like in catalogs. For examination of a pump proposal for a given pump hydraulic system, it is necessary to know the performance of a pump and system curve and system installation curve. The system curve determines the amount of energy Y, which has to be put to liquid by the pump in the given rate of flow Q, considering hydraulic pressure losses that create when liquid flow through the pipes. The system curves describe all losses in the pipe work. This is why it is important to design the correct diameter of pipe relative to the flow. Installation system curve expresses the relationship between energy Y at the beginning of the pipe and flow rate Q. Pressure loss is calculated from the Darcy-Weisbach formula. So H is equal to the lambda coefficient of friction loss over diameter of the pipe times the velocity squared over 2 times acceleration of gravity, when the speed of the water will be expressed from the continuity equation right here, which is a cross-section area times the velocity. After this substitution for calculation of the pressure loss is the simplified formula, which is equal to the resistance coefficient times the length of the pipe times Q squared. Pressure loss in pipe depends on coefficient of friction loss lambda, while depends on physical properties of liquid, geometric parameters of pipe, generally on regime of flow, Reynolds number, and relative roughness of internal surface of the pipe. The graphic shape of friction curve for turbulent regime has this quadratic shape. When to the value of friction loss we add the pressure energy, what is necessary for transport from the beginning of the pipe to the end. So this is my pressure energy. The vertical difference of these 2 points, or in case of transport of water from the well to the water storage, the vertical difference of water level in the well and water storage is ZG. So that's the difference in the elevation we added here in this case. The pump operating point is determined by the intersection of the system curve and the pump performance curve. So this is the pump performance curve that we said, system curve, and in the intersection is my pump operating point. Pump operating point ought to be in the area of maximum efficiency of a pump. What is optimal situation? Design of pump is correct and economic in case when efficiency of pump achieves 0.8 from the maximum efficiency. So this is my system curve, pump operating point is right here, and that's my efficiency curve. So for each configuration, pump pipes and distance of water levels will correspond only one possible operational flow rate QA. In general, this flow rate is not equal to the optimum flow rate QOpt, where the maximum efficiency is. If for a design pump we give unexpectedly different flow rate with a value greater than 20%, it is necessary to choose another type of pump.